Okay. Welcome, honours students, to the most fun part of the honours course, statistics and methodology. I'm really, really happy to be here today, giving you the first seminar for the year, and my hope is always that in doing this seminar, we will actually learn some new things. Usually what happens is you guys ask some really hard questions and I have to go and learn something new to try and answer them. That's my definition of fun. So I'm really open to hands up, asking questions when you're not following something. There's no such thing as a stupid question here. We're all learning. I know enough about statistics to know how much I don't know, which is quite a bit, right? I don't have a stats degree. I came to my kind of current research having done a standard, pretty standard psychology PhD in experimental psychology applied to the law. And I didn't have a lot of knowledge apart from your basic out-of-the-box SPSS style, general linear models. So I knew all about ANOVA, really knew quite a bit about it, but didn't know as much as someone who would have done a stats degree who would have actually had to derive all the proofs associated with actually making an ANOVA model work. So I've come to my knowledge of statistics in a really haphazard sort of way, and now I'm doing mathematical modelling. So I actually build models and I test them and I fit them to data. So they're not standard. They have to be made from scratch. And that means I've had to learn a lot of maths and I've had to learn a lot of programming and a lot of stuff that I never thought I'd ever learn. So I'm living proof of the possibilities that you guys have ahead of you in terms of where you want to go. And I don't think that any of you should be sitting there thinking that you can't learn more about really interesting and useful and valuable things. So how many of you have come from another university where maybe you didn't learn about R? Do not feel bad about that, because R is just a tool. It's just a tool for learning, right? And everything that I'm going to give you is really straightforward. We're not going to throw you into anything that, is not possible for anyone starting in first year, basically, anything that they would be able to do. So I'm not expecting you to, straight off the bat, be able to, write a function, for example. Everything is given to you and it's all really heavily commented so that you can see what each part of the program that we're going to use is doing. And there are things that I'm still learning about R as a programming language. It's really unhelpful. So when it throws an error message, it's just completely not helpful at all. It would just say this doesn't work and you need to work out why. It's really bitchy kind of up itself, sort of, your coding sucks. Go and work it out for yourself. And, that can be really demoralising. But believe me, I still make mistakes in coding that I'm doing. And in fact, you'll probably witness firsthand how bad my coding is when we go tomorrow and do some practical stuff in the computing labs. I'm sure we'll have a million error codes that will be completely impossible to work out, and I'll learn a whole bunch more new things about how people set working directories, for example, and how they might change as a function of some new thing that Windows does, or what how badly a Mac can mess up the situation. So, having said all of that, please don't feel worried about asking questions. Don't feel like you're way behind the 8 ball with this stuff. I've put a lot of effort into trying to make sure that anyone can learn about bootstrapping. So bootstrapping, what the hell's that about? Is that about new footwear that we're all going to learn about? No, it's got nothing to do with footwear. It's actually got to do with a fundamental aspect of statistics that all statistical models are built upon. So everything's about distributions. And all models have a distribution or a set of distributions that describe that model. What's a model? A model is in fact a description itself of a process that produces data. So in all of your statistics that you've been doing so far, you've actually been doing model fitting. Yay, you're all mathematical modelers. Except the difference, I suppose, is that you've been using things that other people have already worked out for you, and you've been fitting models that have already are already there, and you've been doing something which is called plug and play, essentially. It's a good way to describe it. So you take something, you plug it into your data set, it gives you a set of answers, you make some inferences about your hypotheses, etc. But you don't necessarily know whether or not what you've done is happening out there in the population that you're making inferences about. So what this session is designed to do is to do a lot of revision about fundamental concepts in statistics. So it'll take you right back to fundamentals, hopefully, about sampling distributions in particular and the difference between populations and samples. It's also going to hopefully introduce you to R, but also for those who've come through, it'll refresh some of your R knowledge and how to use it. It'll hopefully start you thinking about some more fundamental issues to do with the way that we do research and the way that we make inferences from our data as psychologists, because it's a really hot topic at the moment. It's a big changing landscape. The discipline of psychology has gone through a lot in the last few years. It's kind of like a midlife crisis. I haven't had one yet, but I'm 40, so it could happen. But the point is that there are a lot of changes that are occurring that researchers and people doing research training need to know about. So these changes are things about the way that we do our science, the way that we approach our hypotheses, how open we are about them, how we document our data analyses, how we share that with the world. So we're going to talk a little bit about the implications of that for research practice and also statistical inference. I'll introduce a little bit of heresy in terms of Bayesian hypothesis testing, because I think that's a thing, and I've probably told you about this, would have told you in first year, I've got a bet with Matt Dry, and it's a carton of beer riding on this, that we'll all be doing Bayesian statistics. Now, it was, when we made the bet, we said we'll all be doing Bayesian stuff within 10 years. And he's like, no way, you'll never change the frequentist hierarchy. The Fisher will always dominate. And so we shook on it, that can't be still possible, and I'm actively pursuing it by introducing you to Bayesian statistics, because I figure this is my best chance of getting my prize. So there's a bit of incentive there. But in reality, Bayesian statistics are actually being more often reported in the literature, and you guys are probably, when you do your lit reviews, if you haven't already started, you're probably going to see Bayesian statistics being reported in the articles that you're reading. So you need to kind of have your head around what the hell that is, what it means, how does it differ from frequentist approaches. So we'll just touch really briefly on that. But if any of you are interested in understanding that, more in depth, or you're thinking about using Bayes factors or something in your honours thesis, please come and see me, because I'm more than happy to help you out if you're thinking of going down that pathway, and maybe your supervisor is a frequentist and you want to also convert them. Or not. That might be more difficult than you think. All right, so this is the plan for the seminar. We've got our first session. So this is kind of like a lecture, but as I said, I do want you to actually ask me questions. Then we've got the second session, which is in the computing suites. I think that's right. Is that right? Helen Mayer South. So everyone knows where that is. It's like you've got to go over the road. So I'm saying to people, probably best, and I can see most of you got laptops anyway, probably best to bring your own device, because then I can troubleshoot a million different operating systems. Anyone using Linux? No? Great. So bring them with you. It'll be better. You can take it with you, and then you can actually get things working on your laptop. And then if you want to do bootstrapping on stuff with your own data, then you can do that. So it'll be much easier. There are desktop machines over there, but to be honest, I don't even know whether they've got RStudio installed on them. I think they have. They did have last year, but sometimes RTS just wipe things, and we don't always know if they're there. So that's the plan. Any questions about the plan? Anyone want to change the plan? No? All right. So, most of you are going to set out in honours with a plan. You probably already have a plan for how, or at least some inkling of how this whole research thing's going to work out. You've probably thought about it. Some of you keen beans, I know, have been thinking about it during your undergraduate because you've come talk to me about stuff and I've been like, whoa, slow down there. You know, you've got a while until you get into honours. But, you know, there's nothing wrong with thinking ahead and planning ahead. So some of you would have thought about how this whole thing's going to unfold. Most of you are going to go and talk to a supervisor who wants you to collect your own data. Some of you will be collecting data, using data from other people, and some of you may be doing a bit of both. So you might have a data set from someone else and you might go and collect a little bit more, or you know, there could be a lot of different approaches that you're going to use. But for those of you who are doing primary data collection on a new experiment or new study, you might end up thinking that you're going to get a sample of 200 people but end up with 20. So every year there are a small unfortunate few who go out there with a really big plan to get as much data as they can and then realise that either because it's a special population, although we do try to avoid them in honours, or because of just the fact that first year students really don't want to do your study, you'll end up with a much smaller sample size than what you expected. What I'm going to tell you about and teach you about today and tomorrow will save your bacon in that situation. Because bootstrapping is actually designed to work with really small samples. And that's one of its main advantages, is that there's a minimum size sample that it can work with, but it can help you to actually get around that issue and still allow you to at least, pull back from the brink of disaster and write a thesis with some statistics in it and some inferences in it and some conclusions that can be drawn. So that's a really practical and useful thing. And even for those of you who have nothing mess up, like there's no catastrophe at all, bootstrapping is a part of a family of what we call robust statistics. Now, there's been a move, I think, and a rightful one, towards using robust statistics across all of the statistics that we generate. Because instead of just getting a single number that's an estimated value for something in the population, you get a whole distribution. And when you have a distribution, you can look at that distribution and go, how precise is my result? And really, when we're talking about making inferences, we want precision. So we want to know that the statistic that we've calculated is actually precise and that it's going to generalise to that population. And being able to look at a distribution and see what the spread of that statistic is in that distribution, so what the variance is in that distribution, allows you then make some inferences about precision of the statistic. So even if you've got a massive sample, it's worthwhile actually doing bootstrapping on your data. So most SPSS, I know, has an option in there to do robust resampling or resampling statistics when you actually run an analysis, whether it's regression, a t-test, ANOVA, whatever it is. And once you've done that, you can then look at that distribution and make inferences. So even if you don't have a small sample, it's still a valuable technique to use. Now, what else did I want to tell you? So if you are interested in robust or resampling statistics and these approaches in general, there's a whole world of resources that I can point you towards if you want to learn more. And I think that most of you, if you had Nick Burns last year, he would have actually gone through how to use resampling. I'm not sure, because I haven't had a look at the DRIPA curriculum, but he did it for multiple regression maybe? No? Can anyone remember? No, he didn't? Did he talk about it? Oh, year before. Okay, yeah. So, you would have kind of been introduced to this before, but you might not have recognised how it fits into the broader landscape of statistics and data analysis. So hopefully by the end of what we've done, you'll have a better idea of how it all fits together. So I'm going to introduce you to the resampling approach and explain how it works. Then I'm going to show you how to use the technique on a data set, just for a comparison of two groups, which is a fairly common thing that we do in psychology experiments. Then I'll talk to you about how to interpret a bootstrap procedure, how to interpret the results from that, and then how to write it up in your thesis if you might be using it for that. So let's start first of all with a bit of a definition. And this is a broad definition. This applies to all resampling techniques. Simply put, a resampling technique resamples or recycles the numbers that you have collected in your data set. So they generate, by drawing usually at random from this whole data set, a particular statistic of interest. And that can be anything. So it really is a very flexible approach. You can do bootstrapping on confidence intervals, you can do bootstrapping on correlation coefficients, you can do bootstrapping on regression coefficients, you can do bootstrapping on the T statistic, on the F statistic, on any statistic you can possibly calculate. Anything you can calculate from a set of numbers, you can bootstrap. So it's a highly flexible technique. The really useful thing as well is that sometimes we come up with ways of measuring things that haven't been done before or that are non-standard. So in my own area of research, I've done a little bit of work on confidence accuracy calibration in different types of judgments, particularly unfamiliar face matching and eyewitness judgments. So you might have heard me talk about this in undergraduate, but basically what we're interested in doing in that research is characterising people's subjective judgments in relation to their objective judgments about a particular quantity or a decision. And you can calculate a whole bunch of different calibration statistics, but how do you make inferences about whether or not there's one calibration statistic is significantly different from another in a sample or in an experiment? You need to have an ability to compare those things, right? So one thing that you can do, and that we have done in various papers, is to use a resampling procedure. And now in the particular instance that I've done it with calibration statistics, we've used this thing called a jackknife, which is a resampling technique that doesn't replace the number back into the sample. It's slightly different to what you might be learning about today. But the point is that it's a resampling technique. It allows you to make an inference when you don't know what the distribution of that statistic is in the population. So you don't know the form of the distribution for a particular calibration statistic, but if you bootstrap, then you can build a distribution, and then you can make an inference. So it gets you around that kind of problem. So although we're going to use the example today of the difference between two means as our statistic of interest, bootstrapping can be applied to standard errors, to proportions, to correlations, to medians, to means, to anything. If you can calculate it, you can bootstrap it. The other thing to be aware of is that there are different types of ways of resampling, and the type of resampling that you use, the resampling scheme essentially, has pros and cons. Now that's getting right into sort of applied statistics territory, and I don't think anyone with a psychology degree, unless you've also got a stats degree, would necessarily be able to effectively choose a particular bootstrapping procedure without knowing a lot of the maths behind how things work. So things like whether or not it's a biased or unbiased estimator and how that's all worked out and if there's a correction required. So in that regard, there's a whole bunch of resources that you can use to help you select the right procedure. So statisticians have worked out, which of these is the best resampling procedure to use in this particular situation. And so if you're going down the road of potentially using this resampling procedure approach and you want any advice on that, you can come and see me and I can direct you to the resources that you might need to make those fairly complex decisions. So you do have to think about what the pros and cons of different resampling or bootstrapping procedures might be and what the implications are for your inferences. But as long as you do that, it's a really flexible and useful technique. So you might be thinking, well, why haven't I heard about this? If it's so great, why haven't I heard about this before? Why is it that in statistics we've just been teaching you about correlation, t-tests, ANOVAs, and regression? Those are probably the big four that get trotted out all the time. Why is it that we haven't learnt about this first? Simply put, it's because bootstrapping, although it's really straightforward and simple and logical, years and years ago when Fisher developed a lot of the tests that he developed, they didn't have computers. Or they did, but they were the size of this room, and you had to have a stack of punch cards, and you'd go down, you'd feed in the punch cards, and you'd get a result. There just wasn't the computing power to really do what we're doing here in bootstrapping. It's a computationally intensive process to do this resampling to build a distribution. It's not that computationally expensive, but it can be. So it simply has a historical accident, basically, that we haven't taught people this before. But if I were designing a statistics curriculum, and I don't, I obviously just teach into bits of it, I'd actually start with this. Because this whole approach is the way that those distributions that we rely on for the models that you've been taught about, so the T, the F, all those different types of statistics. This is how they've actually built those distributions so that you can make probability inferences on the basis of those statistics. So, in fact, if I had my way, you'd learn about this first, and then you'd learn about all the different vagaries and varieties of types of tests and how they map onto types of data that you might collect. But anyway, as it stands, this is how we're doing it. So as we've got, I've got enough computing power here, although this poor old machine is just about dead. So, I've got more computing power here than they would have had in the 1970s, like, ever. And it's so cheap now to just buy a super fast GPU off the shelf. Most people, you guys have probably got better laptops than I have, so you could easily run these procedures without any issues. But because it wasn't like that years ago, it never got taught, and it's sort of stayed that way, which is unfortunate. And there's probably not that many psychologists who actually even know about, where the statistics that they use come from. And I think that's a real indictment on the discipline. So anyway. So I just want you to take home this knowledge. These methods relate directly to the key ideas of statistical inference, so that you've already learnt about. You're not actually learning that much new. I'm just pulling back the curtain a bit so you can see what's going on behind what you already know. So if you know about what a sampling distribution is, then you already know all this, but it just hasn't been made explicit. All right. So here's R.A. Fisher. We actually have here at the University of Adelaide, just as a side note, if you're interested in statistical history, we have the R.A. Fisher Library, which contains a lot of the correspondence and notes that Fisher had while he was developing different tests and research programs, because he was actually part of CSIRO, and he is in fact buried over at the cathedral. And it's a really interesting thing to go back and read some of those notes, because Fisher was developing the statistical tools that have now been adopted worldwide for making inference about data. But it wasn't a straightforward linear process at all. It was very much debate and back and forth and compromise, and making inferences based on this particular property of this approach versus this one. So I really like this quote because it really highlights the point that I'm trying to make. So Fisher said, actually, the statistician does not carry out this very simple and very tedious process, the randomisation test, which is in fact bootstrapping. But his conclusions have no justification beyond the fact that they agree with those which could have been arrived at by the elementary method. Basically what he's saying is, without knowledge of the shape of a distribution of a statistic, you cannot safely draw any conclusions about the data. That's the model. Without a model, you cannot draw a conclusion about the data that you've got in front of you. So this illustrates the point that this resampling from a small sample to build up a bigger sample is in fact the basis for all statistical inference that has proceeded from there forward. So just to give you a really, bring home the point of the value of this approach, why do we need this approach to making inferences about our data? There's three things. If we've got a small data set, and let's be real, there are some data sets that are exceedingly small because some people are hard to get a hold of. So this is the unique problem that most psychology researchers face. There might be a population of, say, in the world of 300 people, for example, who are super recognisers. Let's use that example. So there's these people in the world that can recognise a face, someone they saw for half a second 20 years ago. They can see them again and say, oh, I know that guy. That was so-and-so that I saw 20 years ago. There may be 300 of those people in the world. You can only test 15 of them. You can only get access to 15 of them. But you still want to find out how the hell do they do what they do. So you've got that small data set, and you still need to make inferences from that small data set to the rest of that population. Now, 15 people, that's not really enough. You can make them do repeated measures. That can improve the amount of data that you've got, but you might only have them for a few hours or even 20 minutes. Does that mean you should abandon the research project? No. You can use this approach to try and still make inferences based on that small data set. I'm going to show you in a minute how this works, but if you've got skewed data sets, so you have a small data set, but it's also really skewed. It's a bimodal distribution, for example. You just haven't been able to get any of the sample in the middle. You've just got these two peaks in your distribution. Or you've got everyone pulled up to one end and you haven't been able to sample the tail of the distribution appropriately. Bootstrapping can get around that problem as well, and that's via the law of large numbers. So the fact that as we gain more items or bits of information, the distribution becomes more normal looking. So we rely on that really heavily in this approach. And as I said before, there are statistics with unknown distributions. We actually don't know what the model is that's generating the data, but we might have a heap of it, and we want to know, okay, if I can resample and reproduce a distribution, what does that actually look like, and what sort of tests should I be using to make inferences on the basis of an unknown, of that distribution? So if you can build a distribution, that can be really useful as well. Any questions so far? No? All right. The other problem, so how many of you guys have been taught about what to do when you have messy data, i.e. skewed, kurtotic, ugly-looking distributions? Get rid of some of them. So you've been told, if you've got a long tail, exclude the people in the tail. Yep. What other techniques have you been taught about? Yeah, up the back. Transformation. Yep. Yep. Log 10. Yep. They're really common ones. Try and mirror, flip the distribution the other way, then take the square root to try and produce a normal looking distribution. So what happens to your data when you apply a transform like that? Yeah. So how do you interpret an inverse transform square, like an inverse square root transformed score in relation to, say, I don't know, number of alcoholic beverages consumed, or some original scale of measurement IQ? You actually can't do it. You cannot take that. You can do your statistical significance testing and you can say that's significantly different from that, but that's all you can say. Because you've transformed the data, you no longer have that original scale of measurement now represented in that distribution. So you've got it flipped around and inverse transformed, and so you cannot actually say by how much that is different, or practically what the effect size is really if you're comparing two groups, because you've destroyed the relationship there between the two things. So transformation of data is often put forward as a workaround. But I would say that it's not the best approach to use because of that lack of interpretability then that you have in the data set. So bootstrapping is one way to try and get around that problem as well. The other issue, so none of you said anything about this, but one of the things I was taught as an undergraduate when I was doing my honours at Flinders was, okay, if you have really skewed data and your distributions are not normal and you can't safely then apply the model that you want to apply because the assumption is normality, try using a non-parametric test. So non-parametric tests are really great, and that means in that you no longer have this issue then of having to worry about that assumption of normality. That's knocked out. So a non-parametric test essentially is a data transform approach as well. But what it's doing is it's taking your lovely distribution of data, or not so lovely, as the case may be, turning it into a set of like ranked data from highest to lowest, or whatever it might be, and then using that to calculate a statistic, and then using that to make an inference about significance. One thing that will do is destroy the differences between each of the scores in your distribution. As soon as you rank something, you're now getting rid of those differences. So an IQ of, say in a distribution where you've got an IQ of 100 as being the highest, and then the next one down is 89, there's a difference there. But in the ranking procedure, you've just got highest, next highest, and so on and so forth. So that relative information is now gone. What that means is you also reduce the power of the test. So you no longer have that additional information to be able to determine whether or not you've got a difference between your groups. And therefore you're less likely to, in fact, find a significant difference. So non-parametric tests are usually less powerful than parametric tests. And so there's a cost there, at least if your main kind of goal is statistical significance, which I would argue is not what your main goal should be. Okay, so just to illustrate that, this is the data set from the reading. And sorry, you won't work with this data this afternoon, you'll work with it tomorrow, because we're not going to do the practical bit until tomorrow. But this is the Sarah Beanie fan club data. So the real estate data from the reading, the right and field reading. Don't worry if it's Swahili at the moment. On my uni, there's a PDF reading about bootstrapping, and the example for tomorrow is basically us working through that procedure. And this data is taken from that paper. So what you've got are the values of houses, I think in pounds, but I'm not 100% sure. Probably is in pounds. So these are the values of the houses that have been sold by the Sarah Beanie Fan Club Real Estate Agency. And you can see from this histogram that is not a normal distribution, right? You describe that as a bimodal distribution. So if you've got a distribution like that, there's no way that you can use any kind of standard parametric test because you'd violate that assumption. And what the standard advice is, or at least when I was going through honours and doing research, what the standard advice of a statistician might be would be, okay, well, there's no way you can do a parametric test, do a non-parametric test. So rank the data. So this is the data that's ranked, and you can see what's happened. You've still got a really ugly looking distribution, but essentially what you've done is you've flattened everything out. So you haven't got that difference now that you had before. You've just got this fairly flat looking distribution, which then allows you can actually then go and do a non-parametric test with that. So the point there is that you've modified the distribution, but you've also removed information. And that means that you're going to have less ability to infer or make inferences about significance. Okay, so any questions so far about what we've talked about? Yes?
Just confirming.
Yeah.
Are you suggesting that bootstrapping allows you to get around both the transformation of data and also the linking of data problem?
Yep. So both of those things are knocked out. But I'm not saying that doesn't mean there are other problems. So it's too good to be true, it is. So as we go through, I'll highlight some of the disadvantages, obviously, and talk you through some of the reasons why you need to think really carefully. And this goes for any statistical analysis, but you need to think really carefully about the inferences that you're making and the conclusions that you're drawing and what the model is that you've used to generate the test statistic, and then what that inference should be. But without jumping ahead too far and, ruining everything, what I'm going to do now is we're going to do some manual bootstrapping. Now, over the years, I've invested in the School of Psychology at the University of Adelaide has invested a lot of money in these teaching materials. Normally, I'd give out envelopes with numbers in them, but today I didn't have time to get the envelopes and cut all these little bits out, so we've just got numbers. What we've got on this sheet is a column of two sets of numbers, two columns of numbers. The first set is from an applausometer from the Awesome Ukulele Band, and then the second set of numbers is from the Angry Hippies. So this example was developed by one Dr. Rachel Stevens, and Rachel went along to the Fringe, or was it Womadelaide? I think it was Womadelaide. She saw two bands, and she was like, oh, maybe I could make this into an awesome statistics class example. And I've kept it out of absolute admiration for Rachel's creative imagination when it comes to examples. But what we've got are these two bands, and we've got scores on the applausometer from people. Or maybe it's from they might have done this many shows, actually. So for each show, we've got an applausometer score. And what we're going to do is we're going to manually bootstrap from these two distributions or samples. So the first one is the Awesome Ukulele Band. The second one is the Angry Hippies. The hypothesis that we're testing is, did the Awesome Ukulele Band excite the audience more than the Angry Hippies? Very important market research for these two bands. Or something. I really should update this, but Rachel did such a great job. So the only difference here is I couldn't colour print it either. One's in italics and one's in standard font. So if we run out, just maybe might have to share the numbers around a bit. But maybe do it in pairs. So that might be a good idea. So once you've handed those all out, gonna do bootstrapping. Oh. Oh, too late. Oh no. Oh. Well, it's not too late. Once you've learnt this, you've got your data. It's not too late. Okay. So has everyone got their samples of numbers? So what we've got is we've got two means, and we've got a mean of 15.07 versus 7.47. And what we're going to do is we're going to try to test our hypothesis using bootstrapping, and essentially we want to produce two bootstrap distributions. So these are the raw scores that we've got on our applausometer. And this is for the awesome ukulele band, and this is from the Angry Hippies, I think. And those scores up there that are represented in that distribution are the scores that you've got in your columns. So the first column is the awesome ukulele band, and the second column is the Angry Hippies. Yep. Oh no! Okay. We'll pair up. Yeah. Oh, there's some spares here. Great. Is there any other spares anywhere? Fabulous. Wow, it's really sad when we get to miss out. So maybe one between two. No one. I'll go and extract some more from. Okay, can anyone else share a sheet? I know they're really fabulous materials that we're using. Anyone want to give up a spare sheet for the back rows? Oh, beauty. Yeah. Yep. Maybe take a photo with your phone. This is an excellent technical solution down here. Thank you. Just saying. All right. So you've got your two distributions of scores. Let's work through what you're going to do with these. So you've got 15 data points in each, and we haven't got envelopes today, we've just got our two columns of scores. But what we want to do is we want to draw a bootstrap sample of 15 scores with the replacement from each of the columns. So, I don't know, envelopes were really fun last year, except people were losing little bits of paper everywhere, and so there wasn't replacement happening. So what you might do is close your eyes and go, that one, and write down that score, and then keep doing that until you've got 15 scores from each of your columns, okay? Or if you're really clever, you could just write a little bit of code in R to do it. how are people going? Once you've got your 15 score, your 15 scores, what I want you to do is work out the mean of your first distribution, of your first lot of scores, then the mean of your second lot of scores, and subtract one from the other. So if you could subtract the mean of your sample for your awesome ukulele band from the mean of the sample of the Angry Hippies band, and then we'll go from there. So I'm going to get everyone to report their means, and we're going to build a distribution. Because it's with replacement. So you imagine it's like an urn and you're pulling out, or a bingo thing, you're pulling out a number, you're saying it, and then you put it back in. Pull it out again, yeah. With replacement, yeah. That's what that means. Yeah. You're replacing, so you could pick the same number twice. So it's random. It's a random. He'll pull it out, write it down, put it back in, and you could pull out another one the same. Okay. Yeah, with random with replacement. Yeah. Okay, so you can see there's a little bit of variability here. So obviously this isn't an entirely random process. And the advantage would be to have a truly random process. We'd see a lot more variance, I think, here than what we're seeing. But essentially what we're doing here is we're building a distribution of means. And then over here, what we can do is then subtract one from the other and produce a difference between means. But before we do that, does someone just want to quickly, because I can't really do this in my head, I could try, just quickly calculate a mean of these two, because I just want to show you something else. So if someone could calculate the mean of these numbers and the mean of these numbers. Presume you can read my messy writing. Who's quickest? 14.94? No, 1.4. Yeah. And other one. $7.9. Okay, let's have a look at our original means from so our original scores were 15.07 and 7.47. Now, that's not too bad an estimate considering we've only got 1, 2, 3, 4, 5, 6 scores there. I can guarantee you that as we continue doing this, this number will actually turn into that number over there. And likewise with this one. And you can go ahead and do that, and that's showing you the law of large numbers. So what we've done is we've essentially built a couple of distributions here of numbers, but then we can also look at the mean difference, because this is really what we want to know about. This is what we want to make our inference on, the difference between the two means of the groups. So let's imagine that we've done that. I can't remember how this goes. All right. Oh, actually, let's go ahead and do that. So go ahead and calculate the difference between the means for each of those. And then I'll tell you what we do with those. So has anyone calculated all of them already? Yep, cool. Do you just want to tell me what they are? 5.74. Sorry, 5. Just 6. Of course.
5.6.
Yep.
6.3.
Yep.
8.06.
Yep.
5.7.
5.7. Okay. So we have these differences, but we need to do something with them. So the next step in the process is actually to draw a histogram. It's as simple as that. We have a distribution of possible differences here. And then from that distribution, we can actually put confidence intervals over the top of it. Now, if this distribution were to contain a plausible value of 0, then we could say there's actually no difference between the two groups. But if it's anything greater than 0, then we can actually say, we can reject the null hypothesis and we can say, in fact, there is a difference between the amount of applause that the Angry Hippies got compared to the Awesome Ukulele Band. It's as simple as that. It's really no more complicated than that process, except that we do it with a computer instead of by hand. But that is actually the process. Now, you can imagine that you could also calculate a whole bunch of correlation coefficients if you were interested in the relationship between two variables. Or you might calculate, you can imagine any other number that you can produce essentially as a function of, correlation coefficients here. So any number that you can produce, any statistic that you can produce from a sample or a couple of samples if you're testing the difference between means or the difference between two samples, you can build a distribution of those things, and then it's just a matter of simple, straightforward inference. It's no more complicated than that. So just to summarise, are people feeling like you want to just keep going, or should we have a break? Are you flagging? Because I'm quite happy for people to go. And you want to break? Okay. All right, so I'll just summarise and then we'll go. You guys can go and grab a coffee, and then we'll give you 10 minutes and you can come back and we'll finish off. Just to summarise, bootstrapping gets around the problem of small and skewed samples. And it's really simple. Like, you can't get much more simple than that. So you're just recalculating the statistic of interest over and over again. You're plotting it, and then you're working out confidence intervals around that statistic. For the relevant statistic here, the confidence interval shouldn't cross 0. If it crosses 0, it means that no difference is a plausible value, and therefore you can't reject the null hypothesis. If it doesn't cross 0, then there is a difference somewhere, and therefore we can reject that null hypothesis. So it's the same weird inference process that you use for your standard null hypothesis significance testing framework. It's just you're doing the inference on a bootstrap distribution. So we'll take a 10-minute break. So I've got 1:08 on this clock here. So if we come back at 1:18, and we'll finish off the day. Okay, we might get started again. So just before we had the break there, we were talking about the process of bootstrapping, and we took you through a practical example of how that works, and hopefully that's illustrated to you that it's, there's no magic here, it's really straightforward. But I guess in the broader sense, I just want to give you an idea of the basic theory behind bootstrapping, because it's of relevance, I suppose, to all of the statistical techniques that you've learnt about so far, and it's worthwhile revising your knowledge of those things. So let's imagine that we've got a sample from the population of things, and these things have a degree of spikiness, and our hypothesis is how much more spiky than the general population of spiky things out there is our sample. Now you can think about this probably in more concrete terms, like let's say you've got a sample of kids and you've tested their IQ, and you want to know, are these children actually from the normal population or are they from a gifted population? Do they have, as a group, are they normally got smarts? Depending on what you think about IQ and whether it really measures smarts, or are they actually really gifted? So we can use bootstrapping not just to test a hypothesis about differences between groups, but also whether our sample comes from the general same population or the same group. So we randomly draw subsamples from this population, and remember, it's sampling with replacement, and it's always a random sample. The random is really important. Without that random, you won't get an accurate representation of the distribution, and you won't end up importantly with a normal distribution. And the size of that subsample usually is of the same size as the original sample. So if you've got 15 things, you draw 15 new samples. So you randomly draw these, and then you can draw a histogram. So you calculate the mean spikiness of your samples, and you've got this histogram, which is called now a bootstrap distribution. So just thinking about it in really general terms, with any psychological construct or measure or thing that we want to know about, you've got the population. So for us, as people who are interested in psychological questions, the whole population could mean the entire population of the world. If we're doing something on vision, or maybe not vision, that's not a good example, maybe we're doing something on consciousness, we'd assume that most people, nearly everyone in the population is conscious, although that's also not, that's a problem. Is there any typically universal human trait? I don't know. Let's imagine there is one. Language. No, some people don't have that either. Anyway, you imagine there's a population you're trying to generalise to, and you don't know what the mean of that or the statistic of that population is of interest. So it's unknown. And when you read most psychology articles, you usually get a sense of what they're trying to make inferences about in the population from the introduction and the discussion, but it's not always clear in terms of the statistics that they've calculated. Which population are they actually trying to generalise to? Because there's a whole bunch of things about generalisation that become very, very difficult if you actually don't have an adequate sample and a representative sample from that population. So normally what we'd do is we'd randomly draw subsamples from that population. In reality, what we do is we draw samples of convenience. It's very hard to actually get access to every single person in the population, although pollsters try and do it all the time. So the upcoming election, you've probably been robocalled, I know I have. They're trying to get a random and representative sample stratified by age group, location, all the various things they think are important. So they're trying to get that random sample from the population. If we're able to do that, then we can produce what's called a sampling distribution. And for some psychological constructs, like IQ, we do have sampling distributions because they have actually gone out there and tried to test really large groups of people to produce a normative sample of people in terms of IQ. So magic happens. When we apply our theory or whatever statistical model that we're interested in, we make an assumption here about what happens to the statistic as you're resampling from the population. And that produces the sampling distribution. And if it's of the mean, we know something about the shape of that distribution. We know it's normal. And we know that the variance of that distribution can be described by taking the standard deviation of the distribution can be described by taking the variance and dividing it by the square root of n. So we know that that's our sampling distribution, and that's how it can be characterised. Now, with bootstrap distributions, you've still got this unknown population out there in the world. And you've got your one little sample from that population, which may or may not be random. And in fact, it usually is not random. But it's not normally distributed. So you can't apply theory to that. You can't apply this assumption about there being a normal distribution in this instance. You have to use something else in between. So what we do is we take a set of subsamples from that one sample from the population, and then we use a bootstrap distribution, which now is akin to our sampling distribution. So it's the bootstrap distribution essentially stands in for the sampling distribution where we can't actually be sure that the sampling distribution is normal. That's essentially it. Okay. Now, obviously, having a bootstrap distribution is really useful because what we can do is then make inferences on that distribution. So if we look at that distribution and we see that it's normal, so it can be best described by a Gaussian distribution, then we can calculate a confidence interval. So remember the simple formula for calculating a confidence interval? Or maybe you don't, but if you don't, I don't. That's cool. You just look it up on Google. You calculate the confidence interval by using your, if you're in fact using your alpha level of 0.05, and you don't have a directional hypothesis, you cut off 2.5% at either end. So you're looking at the interval between the 2.5 and the 95.5 percentiles of the distribution. So that's defining your 95% confidence interval. And you work out, okay, what are the scores in that region? And if those limits contain the known population mean, we can make a conclusion about our sample. So we can say, yes, our sample comes from the population because it's not, the mean of that isn't, or the confidence interval doesn't go beyond what we know about the population mean. So we say it's no more or less spiky than the population of spiky things out there. So in this example, we've made an inference about a sample mean. In the previous example here, we were making an inference about the difference between two means. The point is you can make inferences using this bootstrapping approach, at least to the extent that you're able to produce this normal bootstrap distribution. That's, I know, it is sleight of hand. It is sleight of hand because it's not always the case that you end up with a normal bootstrap distribution, and that's why you actually have to inspect it as part of the process.
Why wouldn't you? Because you're just treating that population, sample population.
As if it were, that's exactly right, it is a sleight of hand. So you're treating it as if it were the population, that's exactly right. That's the right thinking. Now, well, if indeed the statistic is normally distributed, because it's not necessarily going to be. So let me come to some caveats about this process. So, as I said before, this method can be applied to any statistic. It's going to work well in cases where you've got the bootstrap distribution that's symmetrical and centred on the observed statistic. So this means that it's normal and it has what's called a small bias score. So the thing you can do is you can calculate a bias score. This is the difference between the mean of the bootstrap distribution and the original mean in your sample. Now, if they're really worlds apart, then you've got to wonder whether you've actually produced something that's of value, and you certainly might be cautious about using a confidence interval. So what if it's not? So there are different resampling methods, and I think I'm not going to go into a heap of detail about this because it's actually really complex and I don't understand it that well. But there have been ways of trying to produce normal bootstrap distributions, and it comes down to that resampling with replacement process. In that process, you can apply little corrections and things that will bring your bootstrap distribution to look more normal. And Efron has an entire book devoted to how to do that. But the take home really is that if Efron says you should use this particular type of bootstrapping procedure, then use it. Because he would have tested it out, and in fact there are whole papers and whole special issues of statistics journals devoted to demonstrating how this works. So Efron talks about the bias-corrected and accelerated bootstrap, and this supposedly adjusts for both bias and skewness in the bootstrap distribution. And that the BCA is what we will use, and it's one of the many bootstrap approaches that you can use from the boot package in R. So the BCA, whoops, keep doing that. So this approach is accurate in a wide variety of settings, has reasonable computational requirements. I'd say hardly any computational requirements really now. We've got what we have in computers and computing power, and it produces narrow intervals. Take home, just use this. So just to go through, because I think in previous years people have been a bit confused about when we use bootstrapping. So I've gone through this general approach to bootstrapping, and I've given you 2 examples of where it can be used. Obviously only 2 of an infinite variety of ways that you can use it. So in the example that we used with the awesome ukulele band and the Angry Hippies, what we were doing there was drawing a resample with replacement from group 1 and a separate resample with replacement from group 2, computing a statistic that compares the 2 groups, so the difference between 2 means, and then repeating this process hundreds of times, in fact thousands of times, and we'll do this tomorrow, and you can adjust actually the number of times you do the resampling to see how that affects your distribution. Whoops. No more, it's not going to go. Oh. Come on. Next one. And then you construct a bootstrap distribution of the statistic. So in our case, it was the difference between means, and then you can inspect that for bias, for its shape, and use your confidence interval in the usual way. Now, for us, we were interested in, is there a difference between means? So we were looking to see if this distribution contained 0. But if you were doing testing some other type of hypothesis, you'd have a different setup for whether or not you cared about 0 being in the interval. Okay, so how do you report the results of this process? This is just an example. But what you'd normally do is you'd report that to compare the 2 groups, you use a bootstrap procedure, and you could define in there which type of bootstrap procedure. Or if you express the confidence interval with a little BCA as a subscript, that tells the reader the type of bootstrapping procedure that you've used. So you describe, we did a bootstrap procedure calculating the difference between means of our control and experimental group. The control group had a mean of blah, the experimental group had a mean of blah. The 95% confidence interval for the bootstrap distribution was this, indicating that there was a significant difference in the spikiness of 2 groups, for example. So that would be how you describe a difference between 2 means. So it's pretty much in the same way that you describe a difference between 2 means if you were doing a t-test, for example. It's not very different to that. So the other thing to remember is that you probably should actually state what type of resampling approach you've used. And now that we've got the Open Science Framework, you could put up the R code actually up there so someone else could run it again and they could reproduce what you've found with your data set. Okay, let's come to limitations. And I think some of you have already started to think about this, which is great. You still need a reasonable sized sample to do bootstrapping. If you've got five data points, it's probably not really going to work too well for you. So you need a reasonable size. 10 you could probably get away with. 15's better. You know how it works. Obviously bootstrapping can't correct for these two big problems: poorly designed studies and biased sampling from the population. If you have a subsample that you have handpicked for some reason, or they've come into your study for some unknown reason, let's say you ran your study at the beginning of the year and you got all of the really enthusiastic and helpful first year students in your sample. They may be fundamentally different to the rest of the first years because of their enthusiasm and the fact that they self-selected into your study. That's not a random sample, it's a sample of convenience, and so bootstrapping can't correct for that. And you need to still be aware of that when you're writing up your results. So this is a wordy summary, which I'll just skip over. Here's some additional questions that you might have that I've had in the past, so I figured I'll run through them. How many resamples should I take? Theoretical answer, an infinite number, because the distribution is a probability distribution. The practical answer, around 2,000 is usually enough. But people run 10,000 bootstraps, that's fine. Technical answer, enough until the results converge. So tomorrow we'll actually do some bootstrapping, and you'll see how the difference in terms of the number of resamples changes the accuracy of the distribution. Oh, not long, it's like less than a second. So yeah, don't worry about that. You won't need to call up the Phoenix computing, complex computing machinery to do this. It's pretty straightforward. Now, one of the things that a student asked me probably 3 years ago made me nearly want to crawl under the desk and just into a fetal position and just rock. So this student said, couldn't I just keep running analyses until I get a significant difference between my two groups? So if your confidence interval, if you were producing these bootstrap distributions and the confidence interval is bouncing around and going 0, then doesn't contain 0, then 0, then doesn't contain 0, what is that telling you? It's telling you just have no idea at all, and you will, even if you produce a significant difference or an interval that doesn't contain 0 on one run through, if it doesn't happen again on another run through, it's because you've got imprecision in your measurement. It fundamentally comes down to an imprecise measure with too much variability for you to be able to tell what's going on in the data. So this is the wrong question. And it highlights an issue with all null hypothesis significance testing, and an issue that if you could take this on board when you're analysing your own data and your own experiments this year, you'll be miles ahead of the rest of the world. If you could just remember that any subsample from a population is just that. It's a subsample. Any inference that you make on that sample may not be generalisable to the population. So you're highly likely to be misled if you place too much faith in a single sample. And there are problems with null hypothesis significance testing. So if you click on that YouTube link, hopefully it'll take you to this thing called the dance of the p-values. Now, I won't click on it now, I won't look at it now, but when you get time later on to at home, you might do that. Yeah.
So if you conduct a meta-analysis and use your data from other people,
Yeah, you can bootstrap meta-analyses, absolutely. Yep. Meta-analyses are by definition usually more precise, but a really useful thing to do with a meta-analysis, and this, there are statistics that allow you to do this anyway, is to actually calculate precision values, so that you can actually look at a measure and say, actually this measure, even though it's been used across all of these studies, is so imprecise that it might not be useful for drawing conclusions about X, Y, or Z. Yeah. So the problem with p-values is they bounce around, they change. You can get significance on one day and not on the other. People's promotions are determined by significance because, unfortunately, in the past, people have only been publishing papers that show significant results. Now, this is a really, really big problem when you consider the inferences that are made by people out there in the public about whether psychology is a science or not, because it's not very scientific. to just have confirmatory results and never have disconfirmatory results. So where does this leave us? Well, the APA, I think, have been a little bit slow in what they've been telling people to do. So back in 2010 or 11, the APA had a task force on statistical inference. And they basically said, look, everybody, we know that single p-values and null hypothesis significance testing has its problems. So what we want you to do from now on is report effect sizes and confidence intervals, as if that's going to help. Because an imprecise statistic reported as being significantly, different, or an imprecise result is still an imprecise result. And without knowing what the rest of the distribution of those are, you've got no idea really of where it falls in relation to anything else. So I think a better approach is in fact meta-analysis, if you can do it, but a lot of areas there's just not enough data to be doing that either. And there are broader problems with null hypothesis significance testing. The null hypothesis is by definition a point hypothesis. So when you propose a null, and that is your standard against which you are making your inferences, you are saying there'll be zero difference. But what if there's 0.0000001 difference? You have to reject the null hypothesis if you get a big enough sample, because the probability that you then calculate associated with that hypothesis is entirely dependent on the sample size. You can make anything look significant if you collect enough data, including the ability to be psychic. So rejecting the null is based on this belief that there are only two possible explanations for the data. Does that seem right? Does that seem actually plausible when we're talking about humans who are these complex systems that barely any of us understand? And the models that we use as a standard, particularly null hypothesis significance testing, I'm talking here about general linear models, have assumptions that are often not met by our data, and the biggest one is that data are a random sample from the population. They're never a random sample. No psychologist I ever knew, no matter how clever, ever went out and got a random sample from the population. We always use samples of convenience. And we just hand wave away this big assumption in the models that they're actually a random sample from the population. Another problem is that null hypothesis significance testing doesn't tell us what we want to know. So we don't want to know the probability associated with the null hypothesis. We want to know the probability of our hypothesis given the data that we've observed. That's what we're interested in. So why would you care about a probability associated with no effect? It's just completely mental. Sorry, Fisher. Here's a brief introduction to the heresy and a quote from Harold Jeffreys. What the use of P implies is that a hypothesis that may be true may be rejected because it has not predicted observable results that have not occurred. This seems a remarkable procedure. Dang right it does. So why would we bother using that approach? Well, let's not. There are other approaches. So in Bayesian statistics, there are no conclusions. There are no conclusions about a hypothesis that hasn't been tested or data that haven't been observed. Rather, as in the Bayes factor example, probabilities of a hypothesis can be directly tested and compared. So you're actually making inferences about the probability that you would see your data that you've collected, given that the hypothesis is true. So we assess the probability of a hypothesis being true given the data we've observed as a function of our prior beliefs. So not just as a function of seeing the data, but as a function of our scientific model that we have developed that predicts that this is what will happen. That's our priors. And the selection of prior beliefs is a formal process in Bayesian hypothesis testing you'd have to put a lot of thought into. So you don't just take this standard null hypothesis off the shelf, plonk that in and say, that's what I'm testing against. You have to state clearly what you believe the data will look like before you run the experiment, your prior belief of what you'll observe, and then as the data come in, you adjust that belief. So you either believe that your hypothesis is right, is true, or that it isn't true, and that an alternative is true. And that alternative doesn't have to be the null hypothesis, it can be another competing hypothesis. So it's a completely different way of testing your beliefs about the data that you have. So if you're interested in a defensible approach, fortunately, there's software that can help you. So this is where I sneak the veggies into the spaghetti bolognese. And the kids just eat it all up. So we have this thing called JASP. JASP is a free piece of software that you can download right now from the internet that allows you to do Bayesian hypothesis testing in a really nice graphical user interface with no coding required. So you can run your standard frequentist analyses, but you can also run Bayesian analyses alongside of them and produce Bayes factors. And it's free. There's a meta-analysis package within it. So if you're doing meta-analysis and you're interested in using that package, come and see me because I've been mucking around a little bit with it on a data set that I've got. So it will, other great things about it, it will produce APA formatted figures and tables that you can directly plonk into your thesis without having to format anything. And of course, I think I'm going to win that carton of beer. So it's highly likely that you'll start to see papers now where Bayesian hypothesis testing is at least wheeled in next to standard frequentist tests. But I mean, the most important thing for you to think about if you're going to take this approach is that you actually have to have priors that you specify. So you do actually need to know enough about a particular phenomenon that you're interested in or a theory to be able to make a prediction. So it does require that. You can use uninformative priors, but it takes a lot of data to overturn an uninformative prior belief. So that's the cost. But the great thing is, it's free, it's open, and there's no hiding anything. There's no weird inferences, there's no weird stuff that you have to do, or back to front thinking. Okay. So, rocketed through that. So this is just a summary of what we've talked about today. I've introduced you to bootstrapping as a way of making inferences when you can't make that assumption of normality or you have a small skewed data set. And what I think is good about the bootstrapping approach, at least, is that it focuses our attention on the precision of our results rather than this all or none significance testing approach where you're either rejecting or accepting the null hypothesis. The other thing I just want to mention is this open science movement. So how many of you Rachel would have introduced you to the open science framework last year? How many of you are intending on pre-regging your studies? One, you don't know yet? It's okay not to know. Yeah, a few of you. I'd really strongly encourage you to do this, mainly because it makes you think about your hypotheses, it makes you think about your data analysis plan. You have to do all of that before you actually go and get your data. That means that you've already, you've hopefully already done a good job of reviewing your literature. You've already had a really good think about the analyses that you're going to do. And you're not going to be in a situation where you've collected a whole bunch of data but you just don't know what to do about it. So just from a project management perspective, pre-registration, even if you don't do it in terms of the pre-reg challenge or do it really formally like a formal pre-registered report, even just using the open science framework is a good way to keep a track of all of your data and everything else. And if there's no other incentive, there's journals that actually incentivise you to do pre-registration. So you're more likely to get published if you've got a pre-registered study. And they will actually do what's called a pre-registered report where they will review your plan And no matter what your data end up looking like, or no matter what the outcome of the study, they will, if they like the project, they'll say, yes, we'll publish it before you've even collected your data, which is really great. Yep. Yeah, you could do, yep. So we've pre-registered a meta-analysis on the OSF. Yep, absolutely you can. Yep. Yep. So it's for any type of data, really. Yes. Yes. I don't know that I've ever seen anything qualitative. I know that there are. I'm not sure that there's a similar movement in the qual world. That's a really good question. I've never actually even thought about it. Yeah. Yep. Yeah, I think so. Yeah, it's interesting to think about, because with qualitative, you're not really testing hypotheses often, or maybe depending on the type of qualitative analysis you might be, like if it's some sort of like grounded theory or something like that, you might have a theoretical framework that you're putting over that data. But because you're not really going to reject something, or you're not really doing a test of a model, I don't even know how you'd register a qualitative. Who knows? There probably is a similar version of it out there for qualitative researchers, where you can share your analysis plans. Because I could imagine you've got a lot of coding that you do. I know that when I've accidentally said things like, we should do an integrator reliability check on this, when I've done work with qual researchers, then they've just about smacked me upside the head. We don't put numbers on anything. So that, I don't know whether you can do something similar to that, but in a qualitative way, there might be. Sorry. Worth asking your supervisor though, because they might know if there's an open repository for qualitative research. Because other people can find it then too, which is really useful. But there's things around data privacy, which I will just mention. So qualitative research is particularly difficult because your extracts and your primary data are inherently identifiable, right? They're things that people have said to you in confidence. They're not numbers. You can't de-identify very easily qualitative corporal or whatever they're called. So you can't actually easily protect people's privacy in that way. So a difficulty might be in doing it openly, might be in actually sharing that primary data. You might be able to share like what you're extracting from it, but probably not the primary data. Whereas with the Open Science Framework, what you're really working towards is open data, de-identified but open, so that someone else can come along and run analyses again. Because you can put all your analysis code up there as well. You can put all your R code up there that you've used to generate all of your figures and all of your analyses, and someone else can come along and look at exactly how you extracted that information from your data set, which can be hugely valuable, but also a little bit scary. On the OSF. So there's different ways you can upload just an R script file. You can also have all your code on GitHub, and it will flow to OSF directly. So if you do version control and you change something, it'll just flow straight through to that. Those are the main ways. But in the past, what we've done with our projects is we just bang up our script files, so anyone can just download it, and you can get on there and see all the projects that I've done that are half finished. That's the other great thing about it. It's a really open public record to research progress. I would say, I suggest you talk to your supervisor about whether they want you to do this. But I think that if they are game, you should be willing. But one thing as well to check is that you have your ethics approval actually states very clearly that you will be sharing the data in this way. You have to have permission. You cannot share data without people who've contributed to that being aware that it will be up there. So it has to be approved through your ethics. Now, where are we up to? So this is just the reading that will go through the bootstrapping procedure that we'll do tomorrow in the lab. It's not afternoon, it's tomorrow. So that's up on My Uni. And these are some references that if you're really interested in bootstrapping that you might want to get a hold of. I think Efron and Tiburashani is in the library, in the Bath Smith Library. And that's it.